let's kick this off. So, Bent from Basefront.
Yes, thank you. My name is Bent Terp. As you can see, I'm a Senior Solutions Architect in the Basefront group. We've just been acquired by Orange, but I haven't been told to change my slides yet, so I still write Basefront group here. I'll be doing this in English because I work in the Stockholm's office, but I come from Denmark originally, so my Norwegian is like really weird. First, I'll be talking about a customer case, about a new platform that we've built for a customer delivering e-health services. And then I'll go on to talk a bit about the relationship between agile development, DevOps, microservices, and containers. Because I think there is a relationship, and I think there is an answer to the question why. And I think the question why needs to be asked. So, first off, the customer case. We've built a platform for a customer to deliver e-health services on. And this is not a very large Nordic bank that, like Red Hat was talking about last year. This is a large Swedish e-health provider. It's an organization that delivers dozens of different e-health services. They do it to regional authorities. They do it on a national level, so services that span regions. And they also have direct patient services, where patients can log in with their e-leg and change their bookings, or just discover their bookings, because it turns out that a lot of phone calls to health organizations are, excuse me, can you tell me when was my appointment? Now they can log on and check for themselves, or they can even change the dates. So because these people deliver lots of different services, they have like silos for the different service areas. They have separate administrative teams, and each team that are responsible for a set of services, they've typically gone out and hired some consultants to develop, and these people come in using the technology, the platform, the language that they're used to using. So the landscape here at this customer is extremely diverse. Everybody brings their own architecture, their own service platform, and there's basically very little organization overall architecture. An additional challenge is that this is e-health services, so it's patient data we're dealing with. This means that the developers don't have access to production systems. That's a challenge when the developers have to understand why something went wrong in production so they can fix it. To manage all these services developed by different consultancy companies, there is a single operations team. And their challenge was that because there are so many different platforms involved here, there are a lot of different deployment procedures. It's hard to manage. It's even harder when there is little visibility into the actual control plane of the application platform. Again, making the management side much more difficult. We're dealing with national e-health services. So when we were told to build the new platform, the aim was to go for 99.995% uptime. That's a fairly high one. But the real kicker is that there can be no planned downtime. We are not allowed to plan service windows where we expect to have downtime. Ever. Some stretch goals. It would be good if we could also take control of the source code. Different independent consultants developing applications, storing source code at home or on different cloud services. The customer wanted to take control of the investment in the source code. They also wanted to protect the investment they had made in the existing build pipelines. And they were fed up with having no visibility, so they wanted an admin console that would let the operations staff see all the services. Plus, Recruitment is difficult these days. It's hard to get a hold of good people. So, with a modern platform using the new technology or the fairly new technology, they think recruitment will be easier both for them, and it will also be easier to find consultants who will work with them. Yeah, everybody here knows that this means OpenShift. Okay, so we don't have to argue that one. We started out building a single OpenShift cluster, which is what you have here in the middle. I'm not going to talk about how an OpenShift cluster is built. People have done that so many times. But we have an OpenShift cluster taking in traffic from a load balancer. We send off metrics and logs to Kibana and Grafana. And this is the plane where the developers can see what's going on. The OpenShift console allows the operations staff to see what's going on. Services running have a shared file system under them delivered by Gluster. And the developer, the cool guy wearing the hoodie, he pushes code into a source code repository, which then triggers the build. This is fairly normal for an OpenShift deployment, except that some of the components we have chosen to move outside of the cluster. Now, customer says, but we already have a pipeline that is delivering. We already know how to build these binaries. We just need to do some packaging of them. So either the developer or the pipeline can push binary code artifacts or even complete Docker images into a repository. The OpenShift can then deploy images from the repository. OpenShift can also push images into the repository where we can take them out, use them elsewhere. That's good functionality added. But Basefarm, isn't there a risk that test projects in this cluster will use up all the resources and have an adverse effect in production? We could have that. That could happen, yes. Okay, so we need to have a separate production system. That production system needs to be dual site. Fair enough, challenge accepted. So we now have a test cluster and a production cluster. They have different load balancers, and they have different shared file systems. The production system is dual site running in two separate data centers. We push logs to different systems, but it's the same type of interface used. There is, however, a tiny risk during the upgrade of an OpenShift cluster that something goes wrong, either because we did something wrong, there could be a bug, there could be a feature in the documentation that somebody missed. So when you do the cluster upgrade, there is a tiny risk of losing the cluster. Customer could not accept that. So we have two production clusters. A main cluster, which is usually taking the traffic from the load balancer. So this is a normal way in, traffic into the production load balancer, into the main cluster. We still can deploy, we can build images in test, push them to the repository and deploy them in production. Good. If, however, the production cluster fails, if the main cluster fails, thank you very much, don't ever do that again. If, however, the main cluster fails, the load balancer will detect this because the API is not answering anymore. So the load balancer has a sorry rule, which now sends traffic to another load balancer, to a standby cluster. All services are deployed here all the time. They have access, they share the file system for the service. But they're not seeing any traffic, they're just sitting around waiting until traffic comes in their way. So if something were to happen to the production cluster, either on the cluster level or on the data center level, people will be locked out and have to log it back in. That's acceptable. It's a bit of an annoyance with 5,000 doctors having to log in again. But it's an annoyance. It's not the end of the world. Operations will resume on the other cluster. So that's where we stand so far. We've met the requirements of the customer. We've built this. It's an OpenShift delivery in real life, but as you can see, OpenShift is actually just part of it. There are many other components that we've had to deploy in order to meet all the requirements that happen outside the demo world, out in the real world. Things are a bit more complicated. And we hope that this will give our customer a good platform. They want OpenShift, they love OpenShift, but they say it's not, doesn't answer all the needs they have. An example of OpenShift from the real world. Any questions on that? Yes, Netcompany. Yeah. It's identical. Yeah. Because we expect the same amount of incoming traffic. The reason we're not doing that is because then we'd have to have session state shared between the sites, and that was a risk. This way, all the service, if you have a session held, it's held inside a cluster. That's simply to reduce one cluster's dependency on another, and thus reduce the risk that one cluster failing takes down the other cluster. It doesn't solve the problem at the application level. It's not enough.
Was there a special reason why you chose to run the cluster outside instead of CMS, or was it just because you started before?
No, the reason is to have a shared file system that is dual-side. That would be hard to achieve if that shared file system was held inside on one OpenShift cluster. CNS today does not have support for a shared file system in multiple clusters. Maybe Kubernetes will bring that someday, but we're definitely not there yet. Kubernetes is the federated Kubernetes, with a single administrative plane of more OpenShift clusters. But it's still very much something that might come someday. Yes? These are hardware dual-side F5 load balancers. Yeah. I know that F5 has support for OpenShift directly. We're not using that. We're simply using it to terminate traffic and route it into the OpenShift, into the HA proxy. We have two F5s. It's put here. I've put it here in the middle because there is a unit in each data center, and that's hardware failover. So that's session replication and all the things that the F5 brings to the table. More questions? Yes?
What are some examples of the needs not met by the solutions by the customer?
They have expressed wish for persistent data inside the cluster also. We've had a bit of a hard time balancing that with, you want persistent data stored inside OpenShift, but you want it also available if the cluster fails. Not all parts of the organization make the same demands, so it can be hard to meet all of them at the same time. Yeah.
How do you make sure that you actually have set up? Are you using
Basically, we're doing it by not letting the customer out to provision the volumes. So when they order, they have to order the persistent volumes from us, so we create them in one cluster and import them into the other cluster. By hand, yes. For now. We're still starting out. There are improvements to be made, and this is certainly one point where we could improve, yes. The important thing is that the file system is available in both clusters. All right? No more questions? No? Oh.
For the shared file system to be corrupted.
What I don't show here on the slide is that the shared file system, the dual-site shared file system, actually has a quorum breaker which is located in a third data center. So we need to have you need to have 3 data centers in order to deliver the dual-site shared file system. There needs to be somebody outside to protect against the split brain scenario, which is what leads to data corruption. Otherwise, the solution to that is backups and point-in-time recovery.
Because now 2 data centers has to go down to
Yeah. These 2 data centers are in the same country. The tiebreaker is in another country altogether because there are no latency issues required there. But the only way to protect against data corruption is to use continuous backups and have point-in-time recovery. Replication does not constitute backups. Have we, Andreas? Yes, Andreas says yes, we have.
From this illustration, it looks like you have a shared instance and repository between production and non-production. Is that correct?
Yes. The repository is deliberately made as shared between test and production because that is the way for an application to move from testing into production. You do not ever rebuild your containers. And that's basically what we're doing here. Test is pushing images into the repository. Images are pulled into the deployment and production. But I can't just use build artifacts here. I have to use the entire container. Because the container is what has been tested. I'll come back to that one later, actually. Okay. So, lots of people talk about we should all use microservices. Everybody has to do microservices. Containers is really the thing to do. But why? We also have to be very agile. DevOps, we must have DevOps. Can we buy DevOps somewhere? Where do all these things come together? Now, this is my story. It's opinionated. It's provocative. That's deliberate. You may have a different view, and you're entitled to have a different view. So, trigger warning here, people. What I've seen is a conflict in the requirements that business side places on us. Because DevOps team, everybody has to be DevOps. And to be DevOps, the team has to be able to do everything themselves. All the needs, all the skills have to be contained inside the team. At the same time, they tell us to be agile. And being agile as a team means that the team has to be small. So a small team has to be able to do everything. How do we handle that at the same time? One way is to make the everything smaller. So how do we make everything smaller? We narrow the scope. We reduce the scope of the team's responsibility. Make the team be responsible for less of the application. And we should try and make it as simple as possible for the team to do the operation steps they need inside to meet the scope of responsibility. Narrowing scope, I want to argue, can be done by dividing it into microservices. And one way of simplifying operations, in my experience, is to deploy these microservices using a container platform. What does microservice architecture mean, and why does it make the scope narrower? Microservices is a way of decoupling complexity, and those of us who've been around for a number of years have heard this before. We've heard about the service-oriented architecture, we've heard about the message busing. What's different about about microservices? Why do they succeed where the others fail? They do that by being simpler. Because the service-oriented architecture, the base plate of that was actually very complex. The base plate of the microservice architecture is the simplest possible. It is the TCP layer. That is very standardized interface. In microservice, you talk HTTP to it. That is very standardized. It can be done in many different platforms. Much less complexity here in order to deliver the interface. This means that we get independence in a lot of ways that we didn't have before. We're independent of programming languages. It doesn't matter if you write a microservice in .NET, if you write it in Erlang or Java, it doesn't matter. As long as it can talk HTTP. Very few programming languages these days cannot talk HTTP. When we have separation at the network layer, we get independence in the release cycles. We get independence at scaling. We can reuse infrastructure components that we're used to when we're scaling. We can use a normal load balancer to scale parts of the application without scaling other parts. We can deploy a new version without infecting of one part of the application, one microservice, without affecting the others. As long as we keep listening to HTTP requests. So microservices is a good way of decoupling things and making them separate so we reduce complexity. Independent release cycles means that we're more efficient. This is provocative. It's not this simple. But the idea here is that when the microservices have independent releases, then we do many more releases, but we do them with less pain. So we don't have to spend so long on each deployment. And because we can release them independently, each team does not have to sit around and wait for the others to be ready for the big deploy week. Let's get rid of deploy weeks. We're more efficient like this. Microservices is a lot about APIs. An API should be considered a promise, and it's very important that we keep our promises. An API is the promise we make as a team to the other teams that use our microservice. We promise that if you talk to my endpoint like this, then I will give you this reply. As long as we keep that, we're allowed to do pretty much what we want. We can add new features, because what do you care? You keep talking to the endpoint you've always used. It does what it always has. It doesn't matter to you if there are other endpoints available now also. We can make invisible changes, and basically adding features could be considered an invisible change. But when I mean invisible changes, I mean I could go and change an Erlang microservice into a .NET microservice and nobody cares. As long as I keep my promise on the API level. Sometimes we have to break our promises. Usually because we didn't plan far enough ahead. Then we do what is called versioning. We do a new version of the API. When we do that, we need to be very careful. We need to be very careful that the new and the old version can live at the same time. Because they will live side by side for a long time. Now we come into lifecycle management of an API. What does that mean? That means that as long as somebody is still using the old version, you can't take it away. You deploy the new version, you encourage people to use it, you tell them why it's better, you tell them that the old version will go away sometime, and then you monitor usage of the old version. You cannot take it away as long as people use it. You have made a promise. You have to keep your promises. Once nobody is using the old API, then you can take it away and nobody will miss it. So that's basically why I believe the microservices fit well with the Agile and DevOps way of thinking. So what does this have to do with containers? Well, back in the old days, everybody was running their own servers in their own basement. It was fun. It was maybe not always such a high uptime as we could have wanted. This is not a place I've had servers myself, but I have had a server with 1 inch of water in the bottom of the cabinet. It was still working, by the way. So we moved from on-premise to co-location, where somebody else is running a data center. They have diesel generators, they've got backup batteries, they've got air conditioning. It's all white and shiny, there are locks on all the cabinets. But still, each deployment unit is a whole server, and it's taking up quite a bit of space. It didn't matter so much in the old days, because these servers weren't very powerful either. You had 5 web servers, and that meant literally you had 5 web servers. But as servers grew more powerful, it became difficult to really fill them and utilize them. So the next step was the virtual server, which is your operating system in somebody else's hardware. All the virtual servers run their own copy of the operating system on top of the hypervisor. It gives a lot of freedom. You can run different operating systems side by side on the same hardware. But it also is fairly inefficient in that each operating system has its own copy of a lot of things that don't make business value. The only thing that produces business value here is the application itself, the big white dot. All the rest is just waste. So in order to reduce the waste, along came the container. The container is your application in somebody else's operating system. So the container is just the application itself plus the libraries it needs. Mean that we get a 10-fold increase in the number of application copies we can run in the same hardware. Now we've just went from having one big megalith application into having maybe 10 or 15 microservices that make up our application. So we need to deploy 15 times as many units as we did before. Therefore, it's good that the container allows us to stuff many more copies, deployment units, into the same hardware. That's where we are. That's where we stop right now at this evolution at the container level. But still, we have microservices. We have a way of deploying them that's efficient. There's still lots of things we need to consider around here in order to do this. We need to talk about orchestration, how to actually do stuff. We need to talk about how to automate building the application, deploying it. We need to talk about the processes around change management. How do we handle logs and metrics? These things we need to consider are not microservice specific. They're not container specific. It's always been like this. It's the same things that we've been doing for 25 years. Biggest difference here is that logs and metrics are a little more difficult to handle for a container. Because what happens in a container world, if a container crashes, it's not like when your servers used to crash. You can't log into the dead container and look at the error log because it's gone. So you need to make sure that somebody else is taking care of your logs. But other than that, it's the same thing we've been doing for the last 25 years, at least. Some of you may even be older than me, so you've been doing it even longer. Of course, there's help to be had with a lot of this. And the help is, of course, the Red Hat OpenShift platform, which means that you don't have to consider all of these things any longer, because a lot of it is automated by OpenShift. You're still left with the responsibility of your people and your processes. Nobody can take that away. You still have to consider people and processes. That's the difficult part. Technology is a lot easier to change. People are very hard to change. Processes can be even harder. It doesn't matter that you have a microservice agile development department if they need to fill out paper forms and send them by snail mail to a release manager. You still get a slow release cycle. So consider optimizing your processes so that they fit the new technology. All right? Now we come to where I stopped my colleague from Netcompany, why don't we just push the build artifacts into the repository and then build a new container with them? Because we want to treat containers as immutable. Immutable. When you've taken an application and stuffed it into a container, wrapped it in, this is my deploy unit. You don't get to mess with it. The deployment consists of the application. You will typically have a properties, set of properties, pointing out databases, host names, whatever, something that's environmental specific. And then you have infrastructure around it to make sure that it deploys. These are fairly simple, but they always use the same application. In high security environments, with eHealth, we've done banking, payment card industry. There are lots of situations where the developers, for different reasons, are not allowed access to production systems. And that's where I've found that containers are actually most useful. The immutable container to be what I call safely agile. In the development environment, you have the build process, which creates the container. The developer is in full control at this point. The developer comes with the script, the description of how to build the application. He provides the source code and an SSH key to pull from GitHub or whatever. All these things that go into creating the container. The container is then deployed using a test environment configuration into the testing environment. This is where testing is done. When this is okay, when the developer says that I've done what I wanted to do, the tester says it's worked like the business says it should work. Is this okay? Yes? This container is now ready for production, but it's the same container. That very same container is then copied or tagged, if it's inside one cluster, into the production environment. The developer has no access here, but he knows that the container that was built and tested by him is the exact same thing that goes into production. It uses different parameters, it uses different properties, it's a somewhat different environment, but it's the same application, and the differences between the development environment and the production environment are easy to manage. So now the developer at least have a fighting chance of understanding what's happening in production. And when something fails in production, has a fighting chance of reproducing it and fixing it. But it all boils down to treating the container as an immutable object. That it's exactly the same container that we built once, that we test and deploy. That's what I call being safely agile. Yes, question?
Do you have any ways to, that you said that they don't, the developer doesn't download an image which has been injected with something which shouldn't have? Do you have some, like OpenSCAP, do you have some, don't have any responsibilities?
Two answers to that one. First, don't let them choose whatever build image they want. The build image, the build process here also points out which source to image container you use for the building. Keep control of that. Don't let people drag any which container they want out of Docker Hub and use that inside your system. Second, Red Hat has a partner. I'm sorry, this is name dropping, but Red Hat does have a partner called Black Duck, and their business is doing exactly that. Scanning all images and libraries used in an OpenShift environment against known vulnerabilities. To make sure that not just the container that you use for building, but also all the secondary libraries that you use when you build it. All the Maven libraries, all the build artifacts that goes into the application, that all these are scanned for known vulnerabilities, and that the list of known vulnerabilities is updated, of course. So you have safety in what you produce. And they do that by actually integrating with with OpenShift, so that when the OpenShift scheduler wants to deploy an image, then it can be either stopped or warned if that image has a vulnerability in it. And that, I think, is actually a very good way of doing DevSecOps, meaning that the DevOps team work with security built in. Security is not something that we patch on just before we release into production. It's something that we integrate in the way we work and the way we think. Good question. And it's just up. Yes.
It's application tests.
Hmm?
What kind of a test data?
Test data in my world should also be considered immutable. So that every time you run the test, you run from a fresh set, you restore the test data. So that you can run testing, which actually changes the data and measure that. You have a say you were testing against a database. So you can do that inside OpenShift by having a test database server image with known and verified test data. Every time you run the test in the pipeline, you spin up the database server with the original test data. Then you're allowed to do testing, which actually changes the data, but you can still reproduce the tests. Test data should always be production-like. And I completely agree with you, and we've also done this for this particular customer, is that we have an out-of-band process here, where you take a copy of production data and run an anonymizing application on it, so that the test data does not contain personal identifiable information any longer. But it still has the same distribution, the same size, the same complexity as the original data, so it produces a challenging test. But that has to be done out of band here. And it's something that should be done in many more projects, even when you don't have patient data or credit card data. Or consider this one really. Take a copy of production data, sanitize it. Not by deleting stuff, but by anonymizing stuff. Take away the sensitive information so you can use that for testing and have a process for that, so you can keep changing that. So you can always, on a weekly basis maybe, deliver fresh test data into the developers. So because sometimes the problems you see in production, they only come because the volume of data has changed in production. So you need to do this cycle repeatedly also, so that the test data evolves together with the production data. Very good question.
Same question about the traffic level.
The only way of doing that is, of course, talking to a traffic simulator, and they're somewhat easier to build when you're doing API services, because now you have to do an HTTP request to one microservice in the test. You get a reply, and that reply, of course, influences your next request to the next microservice. But it's still easier to script and simulate than clicking around in a user interface. So I think it's easier to write good testing for API services than for user interfaces. Now, we are managed service provider. So we have built this platform for this customer, and they come with their developers. We don't write the code. Together with us, because we provide 24/7 operations for this customer. That includes helping them with all types of application errors that show up on these services, Because we've done that before when they were not in OpenShift, and so of course we want to continue helping with the main operations of the services, not just the platform, but the services running there also 24/7. And one of the okay, now you've asked it. One of the things we've discovered here to be very easy is the rollback scenario, the dreaded rollback scenario, where somebody forced a deployment of a new version Friday afternoon. We've all been there. Never on a Friday, no, but in the real world, it always happens Friday afternoon. And it looks fine, everybody goes home, we're all happy, and then the poor guy pulling a night shift Saturday night, the alarm start rolling in. Talk to the customers on call them. Look, we're going to have to do a rollback here. In the container world, we love rollbacks. Because what is a rollback in a container service? It is a new deployment of an old image. It is so easily built in to OpenShift that we barely even need to involve our operation staff. The customer can do it themselves. Try doing that with classic JBoss deployments. Here you just say, okay, so I want to go back to that version, and it's still stored in the registry. The container image is there. We're just doing a new deploy of it. But for the love of God, make sure that your data model hasn't changed in between, because otherwise your database server is going to be very unhappy. Rolling back data model changes in databases is not funny. Don't do that. Don't even try it. That's one of the reasons we're not doing it that way. But still, the application in the container can be, the new version can be deployed together with a change of the database model. You've changed the schema on the database. If you do that during a deploy, then you're going to have a very hard time rolling back. You need to think of that when you're planning your releases. So you don't do a lot of changes, and we'll make this little change also, which changes the schema.
So what you say is don't do changes to the application.
You have to.
Friday.
You have to. Don't ever do it on a Friday, but what I'm mainly saying is that little change, which requires a change to the database schema, isolate it into its own release. Don't group it together with a lot of other changes unless you really, really, really have to. So when you're changing the database schema, make as few changes along with it as possible to reduce the risk of having to roll back that change. So that's a hard one, but it involves planning, doing a roadmap. It's part of the roadmap of the releases. There was a question over here also, I think. No? Yeah? No? Red Hat got fed up with me, left. Peter's still here. Joachim also. Good. Yeah. So that's about most of what I planned to say today. Jonas, who was leading the session but just left and come back in, he said, "Bent, they're going to talk. They're going to ask you also about the future. What do you see in the future?" Well, I don't know the future, because if I did that, I would be doing the weather report. What I do think is it's obvious that there are some new steps happening in the packaging and deployment process. Everybody's talking these days about serverless. We have to have serverless applications. Well, you know what? Serverless applications, they are not serverless. They're still a server. The cloud is just a bunch of data centers. Serverless, what does serverless mean? That means that it's your code running inside somebody else's managed container. That's what it means. It means you don't have to worry about creating containers. You write code, zip it up, and dump it and say, build a container out of this and run it for me. I don't care. That is a very, very small step away from how the build process inside OpenShift works today. What you do today in with OpenShift is you can just point it at a Git repository. You don't even have to zip up your source code. You just point it at the Git repository and say, build this. OpenShift will clone the repository, look at it and say, yeah, cool. This is a Maven build that goes into Firefly. Okay, I know how to do that. And they'll produce the container. Of course, it's not serverless, because OpenShift is still running on top of servers. But from your point of view, it doesn't really matter. You have to worry very little about the containers. You don't have to worry about the servers at all, or the cluster. Focus on writing the code. So for all intents and purposes, we can call OpenShift a way of doing serverless. At least it's so close that it doesn't really matter. What will happen next? Well, nobody knows, but machine learning seems to indicate that somebody else's code will manage my data. So the fancy robots will actually write the application themselves to match my data model. I still own the data so far. Some robots are going to take over that as well next time. I don't know, but that's as far into the haze of the future as I can see, Jonas. That, my friends, unless there are any more questions, that's all I had to say today. No?